Last time we have talked about the GPU software, how to write a program for GPUs and how the GPU assembly works. Then today we're going to talk about how the hardware can support that type of assembly, that type of software, and if you look at the constraints on the hardware, you probably will better understand why the software is designed that way. And the software definitely makes some sacrifice to fit the requirement of the hardware. So before I talk about GPU architecture, I want you to review the history of development of GPUs and what GPUs are there. I think you must heard of many news articles saying something like the release of RTX 4090, 5090, or B100, B200. So what are those things? And how you can compare one machine with another? Then we can do. You need to have a sensitivity that catches this news and understand how this industry is producing these products and why and what is being improved from generation to generation. So just using AMD terminology as a understanding, so we can see their release date and the GPUs, the product name and their internal name, that you understand which chips are actually the same, like which products actually share the same chip. Okay, so I want to draw a table, then start with release date, then release date, and we have the product name. After that, we have the chip name. And another thing is called family. Okay, family, yeah, or family or architecture. So when did AMD start to first make GPUs? Then how did AMD start to first make GPUs? It's by acquiring another GPU manufacturer or designer that is called ATI, right? So by the time AMD acquired ATI, it was in 2008. Then AMD started to produce GPUs. And by that time, they were using the old ATI architecture. But a few years after that, AMD started to come up with their new GPU architecture. And this is the fundamental of the GPU architecture you see in AMD today. So the release date of this first product is in 2011. So basically 3 years after acquiring ATI. And they published this one called Radeon HD 7970. So this name is not important, but 7970, 7980, 7990. Then you can, from this number, you can tell if it's a low end. This is 70 is a mid range. 80 is already a high end. 90 is probably the best in the product line. Then by that time, the chip name is called GFX 600. Okay, so how to read this number, how to understand this number is the first number is the family, it's the big version. So you can read it as 6.0.0. Okay, so this is a minor number and this is a patch number. So 600 is their big family, and they call it GCN. It's called Graphics Core Next. The next is in terms of the next generation after acquiring ATI. Okay, so this is 2011. Then in 2013, so I don't want to write down this name. It's not that important. It's very old. Then they start to have a new version called GCN2. Okay, and in GCN2, this version is going to 701. I'm just using the most famous one as the name. So one here is probably not that important, but you should look at this one as the seventh most, the biggest generation of their GPUs. What's before 6 is basically the ATI generation GPUs. Okay, then GCN 2 and 1 are not super different. Then a bigger difference comes in 2015. In 2015, we started to have this GPU called R9 Fury X or Fury Nano. And the R9 Fury Nano is a very important GPU to me personally because our simulator MGPU sim was built on this one based on R9 Nano. So R9 Nano is kept being used again and again. Why we select this one is because our lab happens to have that one at that time. And I will keep introducing this one. You'll find analyzing this one is super easy because it runs just at 1 gigahertz, so makes every calculation super easy. And you will find everything is 64, 32, then it's like all the configuration is a power of 2, so it's very easy to analyze the performance of this one. So today I'm basically going to use this one as the fundamental architecture that we'll introduce today. Okay, then this one is GFX 803. Okay, and this is GCN3. I will also give a commercial name. Okay, so they don't really have commercial name, they only have product name here. So the commercial name for their family. Okay, so this is GCN3, right? Then it's interesting that in 2017, then they start to build this chip called RX 480. So what's the chip generation by that time? And interestingly, is GFX 803. Okay, so that's basically saying it's roughly the same chip, but it's produced, it's packaged in another product, and they call it GCN3, GCN4. And by that time, they start to have this product name called Polaris. Before that, they don't really have this commercial name. Okay. Then GCN4, and there's another one called 5580, and it's also GFX 803, and it's just a slightly more powerful one. And they still like sell it as another product. Then after that, let me look at this one. Okay, this is not 17, this is 16. Then in 2017, they start to build new chips. By the way, what's a big difference here is this one is a 28 nanometer technology. But this one starts from this one, they start use 14 nanometer technology. So the chip is actually getting much smaller and saves energy. Also, you can tell R9 series is their higher end GPU, but on this level is not that higher end. Okay, so in 2017, they start a newer generation and they start to call it Vega 64 and Vega 56. And start this version, they start to have 900. Okay, they start to have 900 series. You can tell this is a new series. And although they never really say it's a GCN series, but typically we call it GCN5. It's the 5th version of GCN. And they have, of course, it's called Vega, and they ditched this naming scheme, and the commercial name is Vega. So what's the difference between 64 and 56? Is the number of cores, right? This one is higher end, has 64 cores, and this one has 56 cores. And remember, in the first lecture, we're talking when we're talking about binning, this is basically the same product, but some defect happening here, so they sold it as a lower end product. Okay, it's 2017. Then after this, something interesting happened. Actually, still in 2017, like because NVIDIA has another product line called Tesla product line, right? This is their higher end data center only chip. So AMD is following the same product line, and they start to have their Instinct. They call it a Radeon Instinct product, and they call it machine intelligence MI50 or MI50 by that time, MI25, MI6. There are several products of GPUs. And what's their product line? And is nothing special, but just GFX 900. Okay, it's the same chip, but it is sold in a different product. Then this is only the chip, right? This is a chip name. So 900 and 900 are using the same design, but the memory around it may be different. Okay, and the cooling system may be different. And they may even remove some, say, video encoder from it that is not the essential part to make it a pure data center product. Okay, one chip can be used for different things. Then starting from this point, then they still using 14 nanometer. Then by that time, TSMC started to have 7 nanometer technology. From 14 nanometer to 7 nanometer is a very big jump. It's probably bigger jump than anything else. So they start to have a chip called, I think this is in 2019, right? Yeah, this is called the Radeon 7. And Radeon VII, Radeon 7. So this is the first 7 nanometer chip in the world. Okay, it's actually super small. The chip is super small, much smaller than this one, but the version is still GFX 900. Okay, by that time it's basically still GCN 5, but they don't say GCN 5 anymore. Okay, so Radeon 7, you can see is not following any like numbering system like 8 or 9 here. And it's called 7 because it's a 7 nanometer technology. And it's actually a solo only GPU by that time in this family. So it's a very weird position that the chip, if you know the die size, is actually very small. That's because they're still producing the same chip, right? But using a new technology, making the chip really small. I mean, the AMD still want to make big chips, but they find problems. The scalability is not working anymore, so they cannot really squeeze in a lot of resources in a larger chip. If I remember correctly, this is 300 millimeter square or something, but highest end is 600 millimeter square, about that size to 800 millimeter square. So they cannot really make large GPUs. Like if they make large chips, it will, like, the communication latency will be too high. We'll see why the communication will be too high in that time. Then they start to say, okay, we cannot really use one product line for the two different market, right? So one market is the gaming market, and one market is the data center market. So they start to have different product lines. So that time, GCN 5 and continue is the last generation for GCN. Then by that time, GCN start to split into two products. One is called RDNA. And R here stands for Radeon. It's mainly for gaming, graphics market. And on the other side, they have CDNA, which stands for compute. Okay, they start to use different architectures to work on two different markets. Then it's 2019. That's not too far away from us. Then what's the generation after that? Then they start to have this RDNA, first RDNA that's in 2020. And the first generation of RDNA. And the chip name is called GFX 10. This product is the 10th generation with one's minor is 10.1.0. That's their version number. Okay, and this is the generation called 5700 XT or XTX. By that time, this is the product. Then the 10 series, this GPU is only a mid-range or lower end GPUs. Then starting from there, they start to have something like 6900 XT. And this is GFX 1030. It's not a big generation, but there's something definitely changed, and they call it RDNA2. So today, I think we're waiting for the release of RDNA4. Then actually AMD is talking about merging them together back to have a uDNA architecture. And what is exactly uDNA architecture? We don't know. But this is only on the gaming side. On the other side, we have the compute side, right? So by that time, it's still in 2020. The compute side, they start to have this GPU called MI100. This is a rather important chip that is kind of competing with A100, the NVIDIA A100 GPU. And if you look at the architecture name, you will understand what is going on. So the chip name is called GFX 908. So what's going on? This is CDNA, this CDNA1. So what is happening is CDNA is rather a patch on top of the GCN architecture. Okay, so it's not very different. They just, in terms of product name, they change it to CDNA. It's basically still GCN. Telling from, it's still the next generation of their GPU. Then, something actually more important is MI200 series 210 and 250. This is in 2021. And this is GFX 908, not 908. So they are running out of numbers, so they are starting to use hex numbers. Because they already have 10, they cannot go towards another major number, so they're starting to change this number. The fundamental architecture is still CDNA architecture, but starting from this point is they start to have chiplet technology. Chiplet means they have different chips, several chips that is packaged in one product. So they made very big chips, and they have smaller chips that is packaged as if it's one GPU. Okay, then also they start to have MI300 series that is the most advanced today, and they start to have tensor cores. Now, NVIDIA has tensor cores, and AMD also has tensor cores in their GPU, and that changed a lot in the architecture. There are a lot of fine-tunes at these generations, but the main architecture is still following the GCN architecture design. Okay, and we're looking for what RDNA will be, and it's still not there, but probably that's a big time that when uDNA is released, we can make another newer version of GPU simulator to support new architecture. Still today, we are doing GFX 803, and that's released in 2015, so 10 years ago. Then it's definitely, our simulator needs to ramp up with a new architecture. Okay, so just a quick review about the AMD family. Now, I think NVIDIA family is simpler. Now, if you do some online search, you know those generations like Hopper, Lovelace, Blackwell, those are all big generations for NVIDIA GPUs. And they also from the very beginning, they have two product lines. Okay. So today we're going to use the GFX 803 chip as the fundamental chip and start to introduce the main component and how it works. Remember last time we're talking about some API calls, right? Runtime API calls. So how it works is the host program. The host program runs on the CPU, right? Then calls runtime API. Then it runs on CPU and is implemented by the user. Then runtime also runs on the CPU, but is implemented by NVIDIA, right? NVIDIA provides a library. Then the runtime calls driver. It still runs on the CPU, but it runs in the OS domain. privileged mode. And it's also provided by NVIDIA. Also, there are some open source alternatives, but it's mainly provided by NVIDIA, right? Starting from this point, the driver needs to run the kernel that is on the GPU side, right? So this runs on the GPU side and is also implemented mostly by the user, right? So the most critical point here is at this point, we're starting to transit from the driver side to the kernel side. And other than launching a kernel, the driver can also initiate memory copy, right? So kernel and memory copy are the most important tasks for the GPUs to run. Now I'm going to draw I'm going to break it down into two pictures. I think the space is not good enough. So no matter what, this code is running on the CPU, right? This part of code runs on the CPU. Now eventually, when we want to launch something, when we want to say, oh, we want to do a memory copy and we want to start a kernel, we need to send a message or send a command to the GPU side. And the GPU side will take care of will run the command. And this communication is mostly done by PCIe network, right? And it's on PCIe. So the CPU uses PCIe to send command to the GPU. And this is the GPU. On the GPU, the entry point is where this PCIe is connecting to, other than a network interface, is something called a command processor. I don't know the term for NVIDIA here, but on AMD side, this thing is called command processor. Okay, this is a command processor. Now, command processor is actually a small CPU within the GPU. It actually even has its own instruction set, and is controlling the rest of GPU, what it can do, right? Let's start with the memory copy part. The memory copy part is the simpler part, and the memory copy part is the simpler part. So we start with this one. So when the command processor knows, okay, it's a memory copy command, right? What it does is it goes to give another engine that is called the DMA engine. DMA stands for direct memory access, okay? So the DMA engine will take care of the memory access. And typically, GPU contains two DMA engines. So because one can take care of host to device and one can take care of device to host. These two can happen at the same time. And if they're using PCIe, they have no interference. Now you can double the bandwidth. Then the DMA engine is direct memory access, right? So it can directly access the CPU's memory, and typically implemented in DDR technology. It can directly access the CPU memory and to directly talk with the GPU memory. Okay, so the DMA engine is basically a data mover, data buffer that can take data from one side and write data to the other side. And then both sides works. And there can be another DMA engine is doing another stream that is accessing the data, okay, at the same time. So for memory copy, that's pretty much it, right? That's the only thing that we want to talk about. No need to understand too much detail. We just know, oh, there's something that can help us copy the memory is good enough. On the other side, the command processor, if it's a kernel, the command processor will start to execute this kernel, right? So remember, when we talk about kernel, the kernel can go down a few layers deep, right? And that's probably the most important thing that you need to remember, that a kernel, what's the next level after a kernel? It's a block, right? So I also want to introduce some alternative names that are used in different contexts. So a grid is a kernel that is launched, or another way to say it, when we launch a kernel, the GPU forms a grid of threads, Okay, it can be one-dimensional grid, two-dimensional grid, three-dimensional grid. Only terminologies. If you use kernel, it's totally okay. It's just another name. NVIDIA calls things block. AMD calls things work group. No reason, just they want to call it work group. Okay. Then block on the next level is warp. It's typically 64 or 32 thread, right? So a warp on AMD terminology sometimes is called a wavefront, or sometimes it's just as simple as a wave. A warp is also called a wave in AMD GPUs. Then below warp, we have thread. Now a thread on AMD side is sometimes called a work item. And then you may also hear this term called lane. Okay. Then think about lane and wave. Just imagine there's a swimming pool, right? And there are lanes. And what is a wave? A wave goes that way, right? And the wave always is at the same location in terms of the lanes, but the wave goes this way. So there are parallel lanes that are going towards that direction, and so this thing is called a wave. Okay, they go parallelly towards the end of the program execution. They call it wave and they call it lane. So in different contexts, you may use different names. So at this time, we have a grid, right? And our command processor knows, okay, we have a kernel that is running, and it can be break down into some blocks, a lot of blocks, right? So on the other side, what do we have? I'm going to remove this part. On one side, we have command processor, and we have kernels to execute. On the other side, we have a lot of cores. For cores here, in AMD terminology, they're called compute unit. I'll just write CU. Okay, compute unit. On NVIDIA terminology, sometimes they just call it SM or SMX. This is called streaming multiprocessors. Then it's a complex name, so let's just use CU, but I'm still going to use block, warp, and thread. And those are CUs. So CU is a core for GPU, but its capability is much more complex. It's much more capable than a CPU core. Then I just don't want you to get confused that a CU, I say, it's equivalent to a core, right? Remember, Vega 64, Vega 56, they are quick numbers for number of compute unit or number of cores. Then, but if you look online, you may hear about another term called CUDA cores. And that's a totally different thing. We'll introduce what they are, but they are not compute unit. What you can see is here is typically thousands of CUDA cores in one GPU. But at the CU level or SM level, there are typically like 60, 100 around this level. Okay. So CUDA cores is something else we'll introduce later. So here, just consider Vega 64 or Vega 56. Then below the command processor, we have many compute units or many cores. So we have the blocks that we want to execute. Now what is happening is this command processor will dispatch these blocks to the compute unit. Okay. Then if we want to introduce a little bit more terminology here, just consider if you have two kernels that want to execute at the same time, what's going to happen? So it's basically the same theory, same method as the DM engine. We dedicate it to something else. Then that something else, if we can have multiple copies of that thing, then we can run multiple kernels at the same time. So what are those things in AMD terminology? They're called ACE. ACE. There are several of them. ACE is asynchronous compute engine. Okay, asynchronous compute engine is responsible for like this. The command processor tells this ACE, you are responsible for this task, this kernel. Then ACE will take that kernel and work on it until it's completed. At the same time, the command processor can assign another kernel to another ACE, and this ACE will take care of the execution of another kernel and dispatch and receive the response from another kernel. Okay, so those are asynchronous compute engines. Then asynchronous compute engines, then we have a lot of compute unit, right? So let's assume we only have one ACE, and this ACE will dispatch those blocks to the compute units. Okay, so imagine in a kernel, if we have 1 million blocks, this is totally okay, right? In theory, this is okay. There's no limitation on number of blocks. Then on the other side, we have 64 compute units. And at this stage, let's just imagine one CPU can only execute one block at the same time. So what's happening here is we cannot really let all the blocks to execute at the same time. And remember, GPU doesn't really want complex control logics. So GPUs do not like swapping or context switching. In CPU, what's happening is if we have 1 million threads, we just store them in the memory. Then the CPU will pick up this one, execute for a while, store it back, pick up that one, execute for a while, and store it back. That's how CPU works. GPU doesn't like that way. GPU works in a way that we pick up 64 blocks, execute, we finish them, now we let them retire, we throw them away. Then we pick up another 64 thread, execute them, finish them, throw them away. Okay. So it's not exactly batches, it's just consider if I can execute one. If I'm a CPU, I execute this one, I get one task, I execute this one. After that one, I get another one from the ACE. Then I'm executing that one, after that one, I get another one. So that means if I have 1 million blocks, if we have 1 million blocks, we only have a small number that is executing at the same time. This makes one thing, that in GPU, you should never expect global synchronization within a kernel. So for example, if in one thread you write for a equal 0, or let's write while a equal 0, wait. Okay, then after that, do something. In one thread, if I want to do this. On the other thread, I write a equal to 1. I set a equal to 1. Another thread. Can this happen? Can this work? Then the quick answer is, if they are within one block, they can work. Because a block is always executed in one core. And at least there are some memory ordering guarantee within one compute unit. However, if you are writing this one in one block and writing this one in another block, you may be in a deadlock. Why is it? Because in one thread, one block, you may be executing this one, right? Then there are 63 other compute units executing something. It's probably also waiting. So the block that is executing this one may not be even dispatched, may not be even executing, right? This one may never get executed because you are still executing this one. You have to wait until this one to complete so that you can start to execute this one. But because of the hardware limitation, you can never run this one. So this is an example of global synchronization. And this never happens. So you should never write this type of program in GPU. Synchronization, or the quick thing that you should remember is, in a GPU program, synchronization can only safely happen within a block level. That's why we have blocks. Okay, block is the smallest, it's the largest unit or group of thread that you can do safe synchronization. Okay, this is the reason, because you have limited hardware and the blocks may never execute at the same time. Okay, any question?
Because I just learned from ChatGPT that for the GPUs they have idling latency by swap the work among the same
Same SM. Yeah.
So why this is just using one work to run on?
Yeah, we'll get there. I'm just making it simpler. So in fact, is one compute unit can run multiple blocks at the same time, right? It can run multiple, but not unlimited. Probably 10, probably 40 different numbers. I'm just making it simple. Okay, we'll go there. Well, that's naturally the next question. That's the next problem. So as we're saying that a compute unit can run more than one block at the same time. So what's the limitation? So how the ACE can dispatch the right number of compute units, number of blocks to the compute unit, okay? Now in that case, we need to go another layer deeper and look at the warp level and see what is exactly the communication between these two. Now what are the limitations? So let's go back, then in this case, we need to enlarge the compute unit, which is the most important unit here, and see how it works. Okay, so here in compute unit, and this is the front end of a compute unit. It has 4 of these things, and we call it wavefront pool. Okay, those are wavefront pool 1, wavefront pool 2, and wavefront pool is our terminology. It's a simulator terminology. We just think it's a proper terminology. Now we use it in MGPSIM and also multi-to-SIM. You can learn from multi-to-SIM. If you look at the AMD terminology, AMD document, you will never see this terminology. They just simply call it SIMD. But this is not descriptive enough. I just call it wavefront pool. Okay. Now within wavefront pool, there are some wavefront slots. Okay, those are wavefront slots. Sorry, I cannot use the word anymore because in AMD hardware, they just call it wavefront slot. Okay, so those are wavefront slot. So what are in wavefront slot? It's basically, it contains some registers like PC, execution mask, VCC, those necessary registers to represent the state of the execution of a verb or a wavefront. Okay, so if there are 4 of them, that means this wavefront pool can hold 4 verbs at the same time. Then in most of the design, in most of the chips, AMD chips, this number is 10. Okay, so 10 wavefront slot in one wavefront pool. 10 wavefront slot in one pool and 10 wavefront slot in one pool. Okay, so that comes to the number of how many verbs that one SM, one CU can handle at the same time. That's 4 multiplied by 10, that's 40, right? 4 multiplied by 10 is 40 wavefront. Then you need to do this calculation. How many blocks can this compute unit execute? And the quick answer is, it really depends on how large is a block, right? Let's say a typical block that equals to 256 thread. 256 thread in AMD terminology, that's 4 wavefronts. Okay, there's 4 wavefronts because each wavefront is 64 thread in GCN or CDNA architecture. In NVIDIA and in RDNA, it's 32. Okay, 4 wavefront. That means 40 wavefront and 4 wavefront. That means 10 block. Each compute unit can handle. So each compute unit can execute 10 blocks at the same time. If you have smaller blocks, you can execute more. So for example, if you have 64 thread, in that case, that's 1 wavefront. Then in that case, you can have 40 blocks, right? You cannot have more. Even you have 32T, it's still a warp. Then you still have 40 blocks executing in one compute unit. Okay? And that's a theoretical upper limit. So we have to have these resources to hold those wavefronts. What are other resources? There are 3 other resources. Remember last time we're talking about S registers, right? And the last time we're also saying there are vector registers, right? And there's also another thing called LDS, local data share. LDS is a SRAM. It's an addressable SRAM in GPU architecture. Okay, so it's a local storage that you can use for like load data to the compute unit and process the data, process, and for many steps, and eventually store it back. So LDS is another resources. So when we compile a program or launch a kernel, we need to tell that how many S registers that are required, how many vector registers are required, and how much LDS is required by that time. So when AES dispatch a kernel to the compute unit, it will also allocate some SRAM space, VRAM space, and LDS space. If there's no space, then that block cannot execute. Okay. In some cases, if you have a really large kernel, like say highly optimized matrix multiplication, if you only have one kernel to run, if you only have one warp can use all the vector registers, in that case, you can only execute one block in your program, in one compute unit. Okay, so basically, as a summary, what's the limiting factor for number of warps that can be executed in each compute unit? There are 4 limiting factors: wavefront slot, S register, vector register, and LDS. Okay, so how large is the vector register? Then the vector register is 1024 multiplied by 64. So we can allow 1024 registers that to be used by each warp, by each thread, or we can say, right? Earlier version can have 256. Now GCN probably is still 256. Then in newer version is 1024. Now 64 is the number of lanes because each lane, each thread will have its own vector registers, right? They have to have physical registers to memorize the number. So what's the size here? 64K, right? Now consider each register is 4 bytes long. So the total size is 256 kilobyte only in the registers. That's a huge value as compared to when we talk about RISC-V, there's 32 registers to use. This is a huge number. So that's why I say 32 is a really small number for an architecture. This is massive. Okay, but anyway, we need to, the most important thing is when we launch a warp or a block, we need to allocate spaces in vector register, scalar register, and LDS. Okay, then when we're executing multiple kernels, because there are multiple ACEs there, we can even have fragmentation problem. Let's say we have one part of register allocated, one part of register allocated. Then the rest of space combined may have enough space for one warp, but they're not connected. If they're not connected, there's no way to execute that warp. Okay, so it's a rather complex process here to find the which part of the vector register to allocate to that block. Also, ACE, when launch a wavefront or a warp, it's not only a process of assigning the task. It's a little bit like operating system prepare the memory state for the CPU to execute. The ACE will also say, oh, your register, this register should set to this value, that register should set to that value. So it will also be responsible for register initialization process. Okay, so this ACE, if you only have one kernel, this ACE, when it's dispatched, it may take a few cycles to dispatch each warp. Okay, it may take a few cycles, then it goes to the next one, goes to the next one, goes to the next one. Consider in modern AMD chips, there can be 120 in MI100. It can be even more in MI200, 300. The ACE can be really slow. Just think about 4 cycles in each CU, then 4 cycles for each compute unit. That's a really small number. Then 4 cycles here, 4 cycles here, 4 cycles here. Then going around is 256 cycles, right? 256 cycles, we may be able to complete a warp already. So if you write really, really small kernels, ACE can be a performance bottleneck. Okay, it can be a performance bottleneck. It's not giving the warps fast enough. And we did measure that if proper optimization of ACE can improve the performance. Like not really ACE, just aware of the limitation of ACE so that intentionally write the kernel to be larger to do more work. Each thread to do more work so that the total number of threads is fewer. Then we can improve the performance by a few times. Okay, so highly optimized kernel always need to consider the limitation at ACE. Okay, so that is the execution. That is how the blocks and warps are dispatched. So think about this. After the dispatching, we have everything dispatched here, right? So now each wavefront pool and each wavefront slot are packed with each wavefront pool, each slot are packed with wavefronts to execute. Let's see how these wavefronts are executed or how the instructions are executed. Okay, I'm going to redraw this one because this is gonna be a big graph for the compute unit structure. So let's draw this big figure. This is a compute unit, and we start with 4 wavefront pools. So we have the wavefronts here waiting to be executed, right? So remember, in the first pipeline stage, what do we do? What's the first typical pipeline stage? We need to fetch, right? We don't know the instruction to execute, so we don't know what to do. So we have to get the instruction to execute. Okay, so let me draw this here. This should be here, but I'm going to draw something else there. So that's me write fetch here. And this is the fetch stage, and there's a arbiter. Can I write in this way? This is a fetch arbiter. So what does fetch arbiter? Because you have 40 warps there, 40 wavefronts there, waiting to be executed, right? So which one can fetch? They all have different PC. Which one can fetch? The fetch arbiter will determine which one can fetch. Okay, So it's really a design decision that what's the arbitration policy. And also we have clear evidence that it's changed by the driver. So one time we're doing some micro benchmarking to test what's the fetching and issue, something we'll talk later, the issue policy. And after upgrading the driver version, things are changed. Okay, so this is something driver can control. And what's the typical algorithm that we can use? For example, the one that fetched, that is for the longest time that haven't fetched any instruction, we fetch for that warp. Okay, that's a typical fetch method. Anyway, so the fetch arbiter will select a warp to fetch and send a memory request to the instruction cache. Now when I say cache, I just use the $sign, and cache has the same pronunciation as cache. So it goes to the instruction cache. We'll talk about instruction cache later when we talk about the memory hierarchy. Then, so let's assume that we have something that is fetched, okay? And what is actually fetched into the compute unit, for each wavefront slot, there's actually a L0 cache or L0 instruction cache, or sometimes it's called instruction buffer. So there's for each wavefront slot, there's a certain size that can store some instructions there as an instruction buffer. So instruction buffer are there to be executed. Okay, so let's assume all of them have something to execute. Then the next level, next stage is to get them to be executed. So what's the next level? Is issue. It's the issue arbiter. Okay. Then on one side, issue arbiter has this input that is 40 warps waiting to be executed, right? Then on the other side, we need to know where they can be executed. Okay. So I'm going to draw this next stage as this. It's maybe slightly different from the real AMD architecture, but I'm just showing in a way that is easier to understand. Okay. Remember last time we were talking about superscalar, right? The GPU is also superscalar. How it's superscalar? It's here the first unit is branch unit. Okay. Then there's a scalar unit. Remember, we have S instructions, so scalar unit, right? Then we have the vector memory unit. We have a VALU unit, vector ALU, or sometimes this is also called SIMD unit, but that's just called the vector ALU unit. Then we have a LDS unit. Okay, consider this stage as decode stage. In this case, issue happens before decode, because by just looking at a few bits, we know if it's what type of instruction they are. Okay. And there's actually another unit called global GDS, and GDS is never used. I rarely see GDS instructions. For so many times, I only seen once. It's in a random generator program. And even in newer version of GPUs, the GDS unit is removed. So let's see, we have 1, 2, 3, 4, 5 units, right? That means this is a 5 issue pipeline, okay? Which means the issue arbiter can issue 5 instructions at most in each cycle. So what are the 5 units? And so the issue arbiter always works in this way. In cycle 1, it selects from wavefront pool 1. In cycle 2, it selects 5 out of 10 from wavefront pool 2, right? In cycle 3, it selects from here. In cycle 4, it selects from here. In cycle 5, it selects from here, and so on. Okay, this is round robin. So we have 5 of them to be executed there. Then there comes a critical question. They say, even if this one, we have 10, right? We have 10 out of 5. So which 5 we need to select? 10 out of 5, which 5 to select? Then there are some rules that at least we can get rid of, that we don't consider, right? The first rule is if this wavefront has instruction in pipeline, no, we don't select this one. Okay? If the wavefront is currently executing some instruction in the rest of the pipeline, we don't execute it. This may not be true in very modern GPUs, and it's not true in NVIDIA GPUs. Okay, this is only an AMD style. Then you can see later on how much it can simplify the header handling. Then the second rule is no two wavefront can use 1 unit. This is easy to understand, right? No two wavefront can use 1 unit. That's a structural hazard. I think there's only 2 rules, only these 2 rules. Okay, and then third one is not necessarily a rule, it's a policy, it's a design policy, and this thing can still change. So even if filtering out the waves by these 2 rules, there may be still some rules that there may be more than 5 that we can select from, right? So which one we can select? It's basically 2 and we try issue as much as possible from one warp, or we try to keep them fair, or try to say, last time we issued this one and this time we issued that one. And we have different policies that I can select. Then very likely is more tend to select the one that is most recently issued. Why? It's because we want the warp to execute as fast as possible, so it can retire, can make the space for new warps. Okay. However, this is not always true, and even in the same hardware, different driver version, we detect that this thing can change. Okay, they may use different policies. Sometimes they want to get like a round robin style to be fair. And sometimes they select this method. Okay, so there's no certain rule for the third one, but the first 2 are sure. Okay. Okay, then we have decode stage. We have 6 decoder, 5 decoder, and there's another type of instruction. So we call it special instructions. What are special instructions? Those are wait count, barrier. We haven't never talked about barrier. It's not that important for microarchitecture here. Then end program. These type of instructions, they call it special. It's a synchronization only instructions, right? Those instructions doesn't need to be executed. The issue unit will determine if wait count, if the counter is there or not. Then if we find the counter is smaller than the value, then we don't need to issue that instruction. It will just discard and execute the next instruction. Okay, so at most it can issue 6 instructions at one cycle. That's in theory. Okay, so starting from this point, the BR is rather easy. So you can consider there's a read, execute, and write back pipeline. Okay, for scalar is also similar. Vector mem, we'll talk about it in the next lecture. We'll talk about the GPU memory system. But let's talk about VLU. What is connecting behind the VLU is a group of 4 SIMD units. And that's the powerhouse of the GPU. Those are all SIMD unit. Okay, 4 SIMD unit. The limitation is wavefront pool 1 can only go to this SIMD unit. Wavefront pool 2 can only go to this one, and so on. And 4 can only go here. And actually, right before here, that is the huge V register stage, right? Because we need to read. Okay, but I don't want to draw in this way, so because I want to tell you better about what exactly is happening in the SIMD unit. Just consider the SIMD unit as the ALU for the GPUs, okay, and also vector registers for the GPUs. So what are SIMD unit and how SIMD unit is implemented? So it's implemented in this way. A SIMD unit, each SIMD unit has 16 lanes. Let's draw it here. This is SIMD unit. In SIMD unit, the ALU has 16 lanes. I don't know how many I draw, but just imagine it's 16, okay? How many thread is one warp? 64, right? 64 thread per warp or per wavefront. So if there are 16 lanes here, how many cycles it requires to finish one warp? 4, right? 4 cycles. By the way, when we talk about GPU architecture, when we talk about instructions, especially issuing instructions, we always need to be sure that what we are issuing. Are we issuing thread level or work item level instructions, or are we issuing warp level instructions? Right? So sometimes we talk about IPC, instruction per cycle. We also need to specify what instruction you are talking about. For CPU, it's the same thing. For GPU, it can mean different things, right? So for example, here, everything here we're issuing are wavefront level instructions, warp level instructions. So when we issue one warp instruction from a warp, not a thread. Okay, that means when we issue once, we're executing 64 copy of the same instruction. That means it takes 4 cycles to execute one instruction. So why 4 SIMD unit and why 4 cycles? It's not a coincidence. It's carefully designed. Right? In one cycle, in cycle 1, we issue here, right? In cycle 5, in cycle 4, we're done. In cycle 5, we start another instruction. In cycle 8, we're done. Right? So here, issue in cycle 2, we start. In cycle 5, we end. 6 to 9 is another instruction. Similar here, in cycle 3, we start. In cycle 6, then we finish. In cycle 7, we run. In cycle 10, we finish. Here also in cycle 4, we start. In cycle 7, we end. 8 to 11. Okay, so in theory, if you only have ALU instructions and everything is working perfectly and you fetch fast enough, you can have 100% utilization of the SIMD unit. Okay. This is a SIMD unit, and here you also need to consider a read. So although it takes 4 cycles, right? So we cannot really say it's taking 4 cycles, but we can say in 4 cycles, the first pipeline stage is completed. So what's the pipeline stages here? You need to consider there are some vector ALU register banks. There are register banks. So in cycle 1, let's say in cycle 1, what do? We do read. We read from the register. How many register we read? We read for 16 lanes, right? Then in cycle 2, I will write this is 0 to 15 lane, okay? then 15, 16 to 31, and so on. In cycle 2, we execute. Let's assume we can execute in one cycle time. In cycle 2, we read for the second lane. Okay? Then here, we execute, and this one will write back. And here, we write back. Then read, execute, write, and read, execute, write. It's 3, 4. After cycle 4, this read stage is freed up. Then you can take another instruction. Okay, so that's why I don't want to write a vector register here. It's actually what's happening is like this. Okay. So let's do some quick calculation. What's the computing power of R9 Nano GPUs? So in terms of computing power, we use this terminology or this unit called flops. Then flops, just be careful. There are two ways to write flops. It's one flops, one is flops. Okay, what's the difference? Is this S is capitalized or lowercase? Okay. Uppercase is floating point operation per second. This is floating point operations as a plural form. Okay, this is a common convention, but some paper or some article may use different ways. Okay, look at their definition. When we're talking about computing power, we talk about floating point operation per second. That's the most important number that describes the capability of a GPU. So let's calculate R9 Nano. How many lanes per SIMD? 16, right? How many SIMD per CU? 4, right? 4 SIMD unit per CU. How many CU per GPU? 64. Yeah, I don't think I talked in this number before, 64. So it's just easiest to calculate. So how many instructions it can complete in each cycle? Just multiply these three numbers together, right? So 64 multiplied 64, that's 6096 inst per cycle. That's the theoretical limit, right? IPC. And just careful, this instruction is thread level instruction or work item level instruction. Okay, 4096 instruction per cycle. Okay, then the best number comes. It works at 1 gigahertz. So that's 1 billion cycle per second. So how many instructions per second? 40G. It's not comma, it's a dot. Okay, 4096 G inst per second. Okay, how many operation is each instruction? It's 2 op per instruction. Why? Because this is confusing, right? It takes me a very long time to match this number with the official number of the official advertised number. What is 2 ops? It's basically the MAC, multiply and accumulation. Multiply and accumulation, this instruction can be completed in 1 cycle time and is considered 2 operations. Then that goes to 8.196 ops per billion ops, G ops per second. Or we say is 8, wait, it's a comma here. It's not a, remember, right? this one by this one, right? It's a comma here. It's not a dot. So if I change it to dot, it's 8.196 T-flops. Okay. It's basically 8.2 teraflops. That's the performance character for that particular GPU. Okay. And here we're talking about single precision numbers. Single precision, F32. Now F32 is, a few years ago, F32 is the most important metric, the property. And today, which one is the most important? Like, even at the beginning of this semester, I would say it's probably F16 or F8. Today, it's probably F4. Floating point 4-bit floating point numbers operation performance is probably the most important metrics. Why? Because machine learning, these LLM models today, especially DeepSeek, uses F4. So that describes how fast a program can run. Okay, it's your computing power. And so just to answer that question, what is a CUDA core? CUDA core is a lane. Okay, so how many lanes are there in the total GPU? This number, 4,096 CUDA cores per GPU. Although that's only an NVIDIA terminology. AMD never used that terminology. But it makes sense, like how many threads can be executed at the same time, right? Right? How many threads, like if on CPU side, the number of cores equals to the number of threads that are executed at the same time. So that's CUDA core. Another concept, have you heard of hyper-threading? Like, a few years ago, it's a super popular terminology for Intel CPU. Hyper-threading. It's a super important terminology for Intel CPU. And recently, Intel stopped working on it, and AMD started work on it. But it's still, AMD never say it's a hyper-threading. They don't have a commercial. They don't have a commercial name. What is hyper-threading? This is hyper-threading. What's hyper-threading is here. You have a lot of threads just sitting there, waiting to be executed. And there's an issuer to detect which thread can issue instructions. Okay. Then, earlier year, Intel hyper-threading, we have 2 HT. That means there are 2 threads waiting there to be executed. So if one thread cannot be executed, we execute from another thread. Okay. And I don't know if there are 4 hyper-threading in AMD GPUs today, but what are the number of hyper-threading in GPUs? It's 40, at least 40 if we don't count the thread level. We're even counting at the warp level. It's a 40 hyper-threading machine. Okay, threads that are sitting there and waiting to be executed. Okay, then I know I haven't answered the question about hiding the latency of memory, but next time when we talk about VMEM unit and the cache system, let's talk about how memory system works together with the compute, with the instruction issue process. Okay, there are some interesting design in AMD GPUs.